Hi everyone, in today's video we're going to be working on some problems where you have to find the work done by a constant or variable force, also the work done by a spring. I have set the timestamps in the description below so you can skip ahead if you know what problem you need to work on. Otherwise you can watch the entire video, which is only different problems related to work. So the different problems we're solving in this video are: calculate the work done by a force using the dot product or the scalar product, the work done by a force from a graph, the work done by a variable force using integration, a little explanation on Hooke's law, and the work done by a spring. So let's get started. We have seen in the previous video that work equals force times displacement times cosine of theta, where theta is the angle between the force and the displacement for a constant force. That is a force that is not changing, increasing, or decreasing through time. You can also write this equation as the scalar product of the two vectors or the dot product, force dot displacement. The x component of your vector is associated with the I value and the y component of your vector is associated with the j value. So, to get the dot product of these two vectors, for example, we just need to multiply ai times bi and that plus aj times bj. If we're given the vector of force and displacement in terms of unit vectors like these ones, we just need to find the dot product to calculate the work done by that force. Let's look at the following example. Problem number 1. A particle moves in the xy plane, undergoes a displacement given by d equals minus I plus 2j meters and a constant force of F equals 2I plus 3j newtons acts on the particle. Calculate the work done by the force F on this particle. We have the first vector to be force, which is 2I plus 3j, and the second vector equals minus I plus 2j for displacement. The dot product of the two vectors is just 2 times minus 1 plus 3 times 2. So that equals minus 2 plus 6, which is just 4 joules. Remember that work unit is joules. Now all that is for a constant force. But what if the force changes or varies through time? Let's look at the following graph, force versus x, which will be the displacement on the x-axis, or basically a straight line. Now the force is not constant here, but we actually want to measure the total work done from the initial x position until the final x position. We can try to break down this graph into extremely thin rectangles. You can imagine that the force will be almost constant on the interval of x, and that thin interval will be called dx. If we calculate the work done in that rectangle, then it is equal to f of x, which is the force component applied to the x-axis, times dx. This is just equal to the area of the rectangle. If you think about it, it is just the width times the height of it. If we break the entire area under the graph into thin rectangles and add them all together, we will be adding the area under the graph to find the work done. So we can jump now to problem number 2. A particle is subject to a force F that varies with position as shown in this graph. Find the work done by the force on the particle from x equals to 0 meters to x equals to 5 meters, then from 5 meters to 10 meters, from 10 meters to 15, and the total work done from 0 to 15, adding all of those three displacements. So we can start with calculating the area under the graph from 0 to 5 meters. Since it is a triangle, it is just equal to half times 5 meters times 3 newtons, and that's equal to 7.5 joules. So that's the work done from x equals to 0 to x equals to 5. Then the work done from x equals to 5 to x equals to 10 meters, since it is just a rectangle, is equal to 5 meters times 3 newtons, which is 15 joules. And for the last bit, from 10 meters to 15 meters, it is the same triangle as in the beginning, so again 7.5 joules. Adding the three totals will give us the work done from 0 to 15 meters, which is equal to 30 joules. Now, most likely you will not be getting an easy graph like that. Or if you do get it, you will be solving, you will need to solve it just by looking at the graph. But for some equation or a weird looking graph, all you need to do is integrate your equation to find the area. So the area under the graph can always be obtained by solving a definite integration between 2 points. That takes us to problem number 3. A force F equals 4xi plus 3yj, where F is in newtons and x and y are in meters, acts on an object as the object moves in the x direction from the origin to x equals to 5 meters. Find the work done by the force on this object. So we know that the force vector is equal to 4xi plus 3yj. We need to find the work done from x equals to 0 to x equals to 5 meters. So we can break it into two parts. Since the first integral includes the x only and the second part of the equation the y component, so we have an integral of 4x dx plus the integral of 3y dy. Since the y position is not changing, dy is just 0. So we must only integrate for the x component. So 4x dx is equal to 4, because that's just a constant, times 1/2 x squared. Then we solve for the definite integral, replacing x with 5 meters, and the result is 50 joules. To solve a problem on work done by a spring, we must first cover Hooke's law. For many springs, if the spring is either stretched or compressed, the spring will exert a force on the block that can be mathematically modeled as force equals minus kx, where x is the position of the block relative to its equilibrium position, and k is a positive force constant, or called the spring constant. It is a measure of the stiffness of the spring. In other words, the force required to stretch or compress the spring is proportional to the amount of stretch or compression x, or displacement. The negative sign means that the force exerted by the spring is always directed opposite to the displacement from equilibrium. For example, if the x is to the left of the equilibrium position, which is where the spring is neither stretched or compressed, as shown in the image there, the spring force will be directed to the right. And the same if the position x is to the right of the equilibrium position, then the force will be directed to the left, so on the opposite direction. To calculate an external force applied on the block, let's say someone compresses the spring with an applied force. Any force applied to the spring will be equal in magnitude and opposite in direction to the spring force. If we were to integrate this equation, the external work done by an applied force will be equal to half the spring constant times the change in displacement. So times final displacement minus initial displacement. So we can solve now a problem regarding springs. When a 4 kilogram mass is hung vertically on a certain light spring that obeys Hooke's law, the spring stretches 2.5 centimeters if the 4 kilogram mass is removed. How far will the spring stretch if a 1.5 kilograms mass is hung on it? How much work must an external agent do to stretch a 4 centimeters from equilibrium? So for this problem, we know the first object has a mass of 4 kilograms attached to the spring, and the maximum x displacement is 2.5 centimeters. We have to find the maximum x displacement that the spring will stretch with a mass of 1.5 kilograms instead. So we can actually obtain the spring constant k with the first system of 4 kilograms using Hooke's law. So first of all, we know that the spring force equals the weight, since the spring force is going upwards and the weight is going downwards, and we know that the object is at equilibrium, so they must be the same if we follow Newton's second law. So m times g, which is the weight, equals spring constant k times x, the displacement. Let's rearrange this equation to find k, and k equals 4 kilograms times 9.8 meters per second squared over the displacement in meters, which is 0.025 meters. K constant is then 1568 newtons per meter. Remember that the spring constant is particular to each spring, so we can use it to solve the maximum x displacement. The force, again, we will use weight, so mg equals k times x. Here we can rearrange to find the displacement x, so x equals 1.5 kilograms times 9.8 meters per second square over 1568 newtons over meters, which is our k constant. The displacement is 0.00937 meters. Now the question asks to find the work done by an external agent to stress the same spring 4 centimeters from equilibrium. Remember, the equation is work equals half times k times x final square minus half times k times x initial square. Since x initial is equilibrium, and that means that x equals to 0, that gets rid of our second term. So we just plug in our values, half times 1568 newtons per meters times 4 centimeters square, but in meters that is 0.04 meters square. The answer will be 1.25 joules. So that's it for this video. I hope these problems were useful. If you have any questions, just let me know, and do not forget to subscribe to see any future videos on these topics. Thank you.